Okay, the transformer, well, it's a kind of new model. People think a lot of new progress on the transformer-based models. And even people think, well, the transformer will take over the RNN things and for the NLP world. And there are a lot of new models coming in and a lot of exciting results. So let's go to the transformer. Actually, transformer is the most complex model we have in this whole class. So we will spend 40 minutes for that. Hopefully, we can finish the transformer. Okay, and one key concept here is called self-attention. The idea for a transformer is like we want to use the transformer, we want to use the attention layer to replace the RNN layers we have before. What about the RNN layer doing? Given a sequence of inputs, you can generate a sequence of output at the same length. Now, if you want to use the if you want to use the attention layer to replace the RNN layer, you want to do the same thing. So basically, given a list of input, you will give the same length of a list of output. So that's what we call the self-attention. So the idea is that for each token in the input, the sequence, we copy it to both key values and query. So that's why we have 3 arrows here for each input. T, we just copy 3 times. Because we have, like, given n inputs, because we have n queries, we will get n output anyway. Okay, so then we will get n output. So now the attention can give the same kinds of output as recurrent neural network. Okay, but note that there's no sequential information preserved. If we shuffle the sequence order, you will get the same output elements values. Even change output order has been changed, but the output value has not been changed. Because remember what we do here, we compute the keys values score and apply softmax and weight the sum of the values. So now this one is kind of sensitive to the orders we have passed into the softmax or the weighted sum. So that's a bad thing. If you want to really replace the RNN layer, we need adding sequential information later. But the good thing here is that we can run in parallel. Each output can be run in parallel with each other. In the RNN, we cannot do that because we need to compute the current time, update the hidden state, which is the input of the next time step. So you can run in sequential. You need to do time by time. But now, for the attention, everyone is independent to each other. We can compute time t independent of t minus 1 because all the input is already there. So that's the advantage. So even that the attention layer kind of have the same complexity cost compared to the RNN layer, it's kind of usually it runs faster because it's easy to run in parallel. Okay, so this is the major, actually this is the major thing people want to use in attention layer to replace the RNN layer. Now here's the model. It's pretty, well, it's in the left hand is the sequence to sequence with attention, the encoder-decoder structure. The right hand is a transformer. The reason we put 2 things together because transformer is actually an encoder-decoder architecture. So even that is a little bit different. You can see that you have the source sentences put into encoder. You have state passed into decoder. So let's first see the difference here. So the first difference is that in the sequence-to-sequence, we have n repeated recurrent layers. Now we replace the recurrent layer with a little bit complex transformer block. It's a great one. You have some internal structures we want to cover later. But the key thing is called multi-head attention, which is a different variant of attention layer, but it's self-attention. The second difference is here. Before, in the sequence-to-sequence with attention, we pass into a single attention layer and fit into the bottom of the recurrent neural network we have. But now, here we move the attention layer into the transformer decode block in the middle. See that in the middle. But change it to called multi-head attention. We're going to explain multi-head attention in a minute. The other difference here is that we have unrepeated block. The state is passed to every block, not just the first one. Okay? So the sequence to sequence we put into attention and then treat as an input to the recounter layer. Now we put the attention directly into the decode block and then pass the state into every layer we have. Okay. The last one, because the attention layer cannot take the sequential information, we're adding a positional encoding layer to adding all this sequential information to the input. So the network will know that, okay, I know even that I don't care about the order, but each element is a little bit different, have time information there, I still can get something there. Okay. But beyond that, these two guys are very similar to each other. Like you can see that for the source items, we put into embedding and then add into unrepeated blocks and get the state. The decoder have another unrepeated block, have another encoding layer and embedding layer, and at the end we just have a dense layer to get output. Okay, so transformer is actually an encoder-decoder architecture. Okay, any questions so far? Yeah. So what is a positional encoder? Yes, we will cover every new layers we didn't cover before, one by one letter. But in the overall idea, have you get the big picture for that? So to put it simple, like a transformer is just an encoder-decoder architecture model. But we just replace the recounter layers by self-attention. Conceptually, you can think about this way. So the idea, because like we mentioned that the attention can be run faster because it can be run parallel. Given the same model complexities, attention model should be run slightly faster compared to sequence. So that's one of the major setting point. And then because it runs faster, we can train an even larger data set and can improve the model accuracy at the end. Okay? So now we're trying to explain every component one by one. The first one is called multi-head attention. Like it has been appeared 3 times in the model architecture. The idea here is that we have multi-head. Each head is actually a normal attention layer we have before. Multi-head means this attention layer have multiple small original attention layers inside. And then given the query's keys and the values, every time we project using 3 dense layers accordingly, project to a lower dimension space, and feed into attention layer, the original attention layer, get output, and for all this head, which is original attention layers, we concat all this output together, make it another dense layer for projection to get output. Okay, in math, what we can do here, if you have H head, so if for the ice head, which is the ice attention, we have WQI, which is the projection matrix for query, and also WKI, WVI, and then for the ice head, we project the query, project the key, project the values, fit into a normal attention layer we have to get output OI, which is output of the ice head. Then we concat vertically, now because it's a vertical vector, we concat vertically and project by WO again to get the O we have. This is a multi-head attention. The reason why we want to do that is because if given the hidden size, given the input size D, for example, if we can project the D into a smaller space, like D divided by 4, and learn the attention layer at this stage and the project back and some this back. So we do 4 times. Kinds of have very similar complexity we have for the multi-layer attention before. Like just the matrix multiplication, everything have a similar complexity. But here we have 4 attention layers. We can learn a 4 selection different criteria here. Instead of just 1, because sometimes if this one have 4 concepts, I want to translate this item. It's kind of related to maybe have 4 different semantic meanings. What I can do is yes, I give you 4 selection mechanism. One is I think this aspect is very similar to these items. On the other aspect, similar to that items. So which means I have 4 different kinds of choice. So given the same computational complexity, and now we have more choice, more diverse the selection mechanism here. So make this way maybe even better results. So this is called multi-head attention. If we just give the input, we copy to query keys and the values, we call self multi-head attention. So that is what we used in the transformer model. You can see all this input is copied by 3 times. Okay, so this is the first new layers have for the transformer. Now here, the second one is called position-wise feed-forward networks. It's pretty long name. Actually, it's a very simple thing. It's just like convolution layers. But anyway, so what we do here is that we know the input size is 3D matrix. The batch size, sequence length, and feature size. So what we do here, we first reshape the input into 2D, like just the batch size times the sequence length. We keep the last dimension. And apply to multi-layer perceptron here. Actually, it's a 2-layer multi-layer perceptron. And then reshape back into 3D. But basically, what we're doing here, we create a MLP, which is flat and equal to 4th. That's all. So why we call it position-wise? A position is just a time step. So basically, we have a multi-layer perceptron, the same one, applied to each time step in the input. So let me draw something. So this is, for example, this is a single batch. So this is the time, and this is dimension, this is t. What we do here, we have MLP here, 2 layers, the same thing. Every time we feed in this one into here to get output here. Again, we apply this one into that to get a second one. So position-wise, it's called. A position is just a time. And the reason we want to do a large one because to reduce the capacity. Remember what this convolution neural network we have. It's actually a 1-dimensional convolution neural network. While we're trying to think about that, if you're adding the batch size dimensions, so the batch size time, this is a D. We can think this is one image. This is the channels we have. The one-dimensional covariance, not covariance, convolution layers is actually a convolution layer. For each pixel, I pick up a channel to project to another dimension. So basically, just it is 1-by-1 convolution layers, just 2 convolution layers. But we have a different name called position-wise FFN. That's all about the things. Again, this one will not give you any time information here because for each time we just run by in parallel. So still, this network didn't reserve any time. Okay, remember that we have 2 position-wise FFN in the model. Another one is called add and alone. So we have a bunch of things here. The basic idea here, the add means a residual connection. So here we show block. This block can be either a position-wise FFN or just a multi-head attention. So the input of this block and the output of this block are summed together. So this is a residual network we have saw before. So this is what they call add here. The norm, here we are using something called layer norm. It's very similar to the batch norm we have. The batch norm, we compute the mean and the variance for each pixel across the batch size we have. But the layer norm, we just compute along the feature dimensions we have. So for example, if x is the input, in the batch long, we compute x mean x is equal to 0, which is any elements across the examples we have. But layer long, we just compute the mean and the variance along the last dimension, which is a feature dimension. Compute the mean and the variance, we just get input x minus the mean and divided by the variance and have the scaling alpha and the beta. Then we can just learn about alpha, beta, and that's a layer long. Okay, so we didn't use a batch long, we use a layer long here. It kind of like just a normalization to make the deeper model much easier to train. That's a major thing. So both the residual network and the layer long we can add in very long, okay, stack a lot of transformer block together to make the whole network easy to train. Okay, the last one is called positional encoding. The positional encoding, the idea is like all this add norm positional wise Fn and multi-head attention doesn't take care of all these sequential orders. We want adding something there. So the positional encoding, adding something into the encoding output, adding the time information here. So assume the embedding matrix is X, its L is the sequence length, and D is the feature dimension of the embedding. And then we create the P, matrix P, such that each element is different. Each element is different to each other, right? Not equal, different to each other, but you have some patterns here. It's cosine. The cosine is a little bit hard to understand, but I can, in the following, we will show that actually how to visualize all these results. It's hard to see here, but you can see that for each row, for each time series, we have a sine and a cosine with different frequency. And the sine cosine have a little bit of shift for the period. So which means you're adding some information to the each element of X so that in the later on, the network can realize what it is. So then given the P, and we using X plus P to get output. So just adding something into the embedding layer so that at different position, at different position of the feature vector, different position of the time, adding something different values into the value input. So that's all about that. Okay, so that's all things about the models. The others, the overall structure is clear. It's a sequence. It's a encoder-decoder architecture, and we explain every layers. So, any questions so far? Question.
On the added norm, why is it norm on the last dimension?
You mean why adding a layer alone?
Like on the added norm layer block, I guess. Why do they do the mean across the last dimension?
Okay, so basically why using layer norm instead of batch norm?
Yeah.
But that's a good question. Like it's a kinds of a normalization. It works well here. So unfortunately, I don't know the reason, but I feel like NLP, a lot of NLP tests are using layer norm. I think probably because like for images, what do you think? I guess it's not be true, but you know, there are a lot of guess. But you can, maybe I'm wrong at any time. So what's the difference between image and the text? So image use a batch norm, but now we use a layer norm. For the image, for the pixel you have, so this is the for the height and the width. So each pixel kind of it's a random variable. It's kind of the value can be kind of random. The object can be on any particular position in the image. So in the histogram should be if you think about the variable, the histogram for each pixel should be kind of maybe the same thing. So which is every value kind of like very similar to each other. So which means if you normalize it across this one or across this one, doesn't make sense because they're kind of uniform already. But the images may be different across example to example. Like it's a bird, it's a ship, and the bird and ship color are same, but it's a flower that's different. So text is different. For text, the difference is here. If the their token, and if another token is Berkeley, then the frequency is very different. Like this one is a frequent word, this is also a frequent word, but you can pick up another one. But usually the frequency is different. And in the text, usually you have power law distribution, which is, so this is like the top one words, and this is frequency. The top words take a lot of things here. So make the text have like a very different patterns, frequency patterns. It's unlike to the pixel level things. So this makes kinds of like the normalization patterns different. Okay, so images we normalize across examples. Now text we just normalize across the feature dimensions we have.
What exactly would that like feature dimension represent?
Our feature dimension is like one feature is just item. So this is a dir according to that. And this is like a Berkeley or like called any, like I pick up any, like I don't know if we have any like Canon, for example. So I think usually this one we have more, like the value will be large because the dir appears frequently. If you do updates, the likely this one be updated is kind of more than this one. Every time you do update, you make, I don't know, like you maybe make this value large. So we make this long larger, much larger than this one. The layer long, what the layer long do is like, well, I don't care, like for this one, I normalize this vector, so the element here have 0 min, and one variance 1. So this one have 0 min and 1 variance. So no matter frequency you have, I kind of, each presentation make it more uniform. Otherwise, you have, if you don't do that, this is all the tokens, this is the vector for that. All this one have very large values, this one have very small values. And this one will make the gradients much harder to train. Next week we'll talk about add-on, like because this one have a very large gradients and this one have small gradients. This one cause a optimization problem much harder. If you choose a larger learning rate, because you want to choose larger learning rate, because you want to update like more frequently, but then it maybe make this one explode. Then you have problem. If you make this one be in the proper stage, you need to choose a very small learning rate, or 0.1, and then the update for this one is too tiny. So the canon will not get sufficient update. Normalize make life much easier. So that's kind of idea. Okay. A similar thing, that's kind of similar to given a normal like machine learning class, given a 2D vector, these examples. So this is a feature. You can, if you want to normalize it, either you can make each column to be 0 min and 1 variance, or you can make each example like 0 min and 1 variance. So the way you want to choose it depends if examples are different to each other or features are different to each other. So that's you have different considerations here. So this is called batch norm. This is called feature norm. Okay. Any other questions? Okay. The last one is about how to do predicting. Like, in predicting, we want to predict at time t. Assume we have already the input from 1 to t minus 1, and then we put all this as the memory cell, like just a copy as key and values, not a query. Then given the current input, we copy to both query and the key, and also the value. So then we have a single output here for the current time. And this one will be, if you remember the greedy like searching stage we had before, the output of this time will be used as the input for the next time. So that's why we cannot run in parallel. You have sequential information, have sequential here. Okay, so that's all about like transformer. Let me check the time.